So, oh, nice. Good work. Okay. um, so hello, everyone. I am excited to welcome you all back for the afternoon. We had some great talks this morning, obviously. And we're going to start off with another great bang, I think, here from Rob Axtell. So many of you know Rob already. Rob was the the co-author of Growing Artificial Societies, the kind of one of the texts that we all use from back in the day with Josh Epstein. He works at the intersection of computational, social, behavioral, and economic sciences at George Mason University, where he has really been instrumental in setting up and creating the Center for the Social Complexity that they operate there. Has mentored many PhD students who have come through that program quite successfully, and which is now rolled into the computational and data sciences department at George Mason University. And Rob is going to be, has done some great work modeling economics, systems engineering and operations research, public policy, civil and infrastructure engineering. Many of you may have heard of him for his models of the entire US economy, for instance, in the firms and labor markets represented therein. But today he's going to be talking to us about creating ABMs from extant mathematical models and the notion of agentization. And without any further ado, I'd like to turn it over to Rob Axtell.
Okay, thank you very much, Bill. Appreciate the invitation to speak here. This word agentization, I don't expect anybody has heard it before necessarily, so I'm going to go through what I mean by it. Then that's going to be the focus of the talk, but I'm going to in particular relate it to the idea of inverse ABMs, inverse generative social science models. Okay, so for all of us who work within the ABM world, certainly, and most social scientists in general, certainly have a sense that the kinds of models that we work with usually have this multi-level character. Typically, for example, certainly economists think about the agent level a lot. Maybe, Scott mentioned in the last talk Coleman's boat. Coleman was a sociologist. Maybe he doesn't think about the micro level always, but in the economists, we think about the microscopic level. And then, but there is also the social level. And I've written here, this kind of function F is how we march our ABM forward. How we can get this function G to march the aggregate world forward, unclear. But in the meantime, we have these aggregation operators A that operate across levels. So certainly ABMs are multi-level systems. And oftentimes we have data about either the aggregate level or the micro level, could be both. And then the question is how to infer F. And of course, that's the main topic of this whole workshop. I'm not going to be able to say a lot about that, but I'm going to talk about one specific area where we can substantially narrow down the search process, through this agentization idea. So I'm going to go through that here. And the inverse problem becomes easier, I'm going to argue, basically, in this agentization paradigm. Okay, so what do we mean by agentization? So the basic thought is you just take some model, some well-known formal model about which, for example, there might be theorems proved, even the Arrow-Debreu model, something like this, or it could be a statistical model. So there's some model that exists, it's viewed to be good social theory, say, and we just want to render it with agents. Okay, we just want to render it with in the agent computational paradigm. For example, how might you do that? Well, maybe the model is written in terms of one representative agent. It's a typical kind of a model that we would see a representative agent used in, say, macro. And you're going to model it with a lot of individuals. So you're going to model it. You could maybe use a few types, or you could use every agent being completely unique. It could be that the model solves for equilibrium. That would be normal, certainly in economics. But it might be that when we run our model, we're not going to get agent level equilibrium. We're going to get something more like social steady states. That is, we'll get a macroscopic equilibrium or steady state, but not at the agent level. So this is kind of contra Nash, the Nash formulation of modern social science. Could be that we want to relax rational choice, rational behavioral specifications in favor of things that look more like what happens in a real laboratory setting. So anyway, there's a variety. I'll go into this a little bit more detail, but there's a variety of ways we would want to do this. And the question becomes, obviously, if we're simply trying to reproduce, the results of some conventional model, some already known model for which, for example, maybe there are theorems proved about it, we have now very severely constrained the solution space. And the solution being, what agent rules are sufficient to generate, to reproduce the original mathematical model. I'm going to give some, if this is not clear, I'm going to give some examples here in a minute. But I just want to say, I guess the final point about this general idea is, once we have done this agentization, I mean, we could just stop and say we reproduce the conventional result. But of course, then, because of the great power of computing, we can then start to relax the conventional assumptions and say, and ask questions about how robust the original model is or is not. Now, many of you have seen the following table, both in my own work and with work with Doan Farmer and Brian Arthur's recent work. This is the idea that in almost all the models that we write in the social sciences, there are many dimensions. For example, how many agents does it have? A representative agent model in economics has one agent. How is information dealt with in such models? It could be that it's global, it could be centralized, etc. But in reality, I've written over here at the on the right hand side, complex models might have things that are not like simple models, right? Complex models may say, we have local knowledge or tacit knowledge. By the way, some of you may question whether is centralized knowledge really a thing that's still believed in anywhere? I mean, obviously, there are some branches of social science where we relax that assumption, but oftentimes we do say all agents have access to the same kind of knowledge. Beliefs, they could be homogeneous, but in reality they're going to be heterogeneous. So along many different dimensions here, we think that we want to build more complex models, but we don't know how to do that mathematically. So once again, we solve for Nash equilibrium, or we use game theory to model strategic behavior, but with rational actors. So what this table really just suggests is that we teach graduate students the social norms that we teach graduate students have much more to do with the middle column here, the simple social science world, and we want to move over to this more complex one. And so we'd like to be able to relax things and to relax the conventional specification, but it's very hard to do mathematically. Of course, it's relatively easier, not necessarily easier to do computationally. And then just as a footnote, I just wanted to emphasize that once we have an agentized model, as it were, some of the critiques of ABM kind of dissolve, I think. And just to I'm putting the cart a little bit before the horse, because I haven't shown you an agentized model yet, but I just want to deal with these things up front and say, when people say ABMs are not useful science because anything can occur, I mean, so imagine we take a very well-known model. For example, some of you will know the Akerlof model for lemons, say we teach in microeconomics. Once we've agentized that model, if we show then that a whole variety of things can happen in Akerlof's model once we start relaxing things, is it the case then that is it a critique of ABMs that anything can happen, or is it a critique of Akerlof's model that anything can happen, but rather he actually got the results by assumptions, for example? Now, I'm not saying that's the case for George's model, and I'll talk more about that at the end here. But the idea is that some of these critiques are not robust to the effect that when we build the ABM of the existing model, we can ask the question, we're gonna make agents a little bit sub-rational. Do then all the results fall in the garbage can, or do they stay roughly approximately right? So how brittle or how robust are existing models? There's also the critique, and I was just last week at a DARPA meeting. Those of us around the ABM community, we always get this critique of mostly from natural scientists. You can't really do social science because the underlying behavioral theory is so weak. And so I think that to some extent we can deal with this in the sense of, at least to the extent that people buy into the idea that social science is at all possible. I mean, we can at least do as good a job with our ABMs as we can do with a mathematical model. So maybe have more to say about that at the very end. Now, what about the critique that says, well, there are many agent specifications that are sufficient to generate the existing output? I mean, this is the essence of science, right? I mean, Newton is an explanation of why the planets do what they do. Einstein is a different one. We adjudicate them based on underlying, what we believe to be physical reality or underlying whatever. And so, I mean, the essence of science is to say, here are multiple explanations of an existing phenomenon. Which one is, in essence, the way the world works? One is not, one is. Let's entertain then the one that is and wait for someone to come up with a better version of that down the road. Finally, there's always this, I view it as not very deep, but there's always this kind of Borges level critique of what today we would know as, we used to call them mirror worlds. Today they're called digital twins. That is ABMs that have very high fidelity. They're one-to-one maps. They're almost one-to-one maps of the real world. They're becoming increasingly common. But I think that people will complain. They say such things are not useful. But in fact, when you can run them at 1,000 times or 1,000,000 times real time, they are super useful. And if you don't believe me, I mean, I can give you 100 examples here in Washington where agencies have tried to build things like digital twins, and they use them for real time monitoring or forecasting or something. Okay, so this is just a way to say, if these agentized models, built in this very constrained solution space, just trying to reproduce the conventional results and then generalizing, are a way to address some of these critiques. Here's a first example. Okay, so once again, I just apologize for putting the summary before the examples, but this is just, I want to go through a couple examples now just to give a flavor for the different aspects of this. The conventional supply and demand picture is one we all know from undergraduate school, right? And so the red line here is the demand curve. The red line is the supply curve. The blue line is the demand curve. And what I have here, and this is just a net logo output graph. This is a series of transactions that have happened up to approximately the market clearing price and quantity. So there's a population of buyers, a population of sellers. Well, we often have to abstract from even the fact there's a finite population when we draw the curves perfectly straight. It's kind of almost like there's a continuum of them. Heterogeneous costs for the sellers, heterogeneous values for the buyers. What the heck happens? Textbook has a point estimate, a specific P, a particular Q. Vernon showed a long time ago, my former colleague here at Mason, that you can run experiments where people are not, by their own self-reports, they're not really doing very exotic calculations, and they can get pretty close to the same answer. I mean, always before Vernon's experiments, people said, well, how much information do people have to have in order to compute what is the market clearing P and Q? But in fact, people don't have to compute that. You can still get close to the right answer. There then came on a bunch of work associated with zero intelligence traders, et cetera, also demonstrating that little calculation was necessary. And then, I think that it's also the case what you're seeing here. What the black line shows is that, this is a kind of a glass half full in the sense that, yes, we can get the right kind of quantity coming out, but notice there's lots of price variation. And it would be nice that if this market went from 10 to 100 to 1,000 participants, this price variability dampened out. But we know now from large scale experiments that this price volatility, as it were, does not dampen out. And there's much more to say about this. And I'll just kind of skip it for now. We can come back at the end if there's questions about it. Okay, so when we agentize a model, what can happen? And I've written here, it's kind of this, in essence, it could be that the ABM is just a very special case of the conventional theory, where the conventional theory has theorems about it. And it has, for all symbols of this structure or this, as long as the symbols take on integers or real number values, you're going to get some result. So this could happen. ABMs are just very special cases, right? Every result of an ABM is a theorem. Every run is a theorem, but it's potentially a very special case. Or it could also be the case that that the agent-based models is so general, we can relax assumptions. We can do a lot of things that are hard mathematically. It could be this kind of result. And of course, more realistically, it's probably going to be this kind of thing, right? Where there's some things that you can do with a conventional theorem-based approach that works. Some things you can do with stats we can't do with agents, et cetera. So some overlap here. I'm going to give a couple examples, though, of things that are more like this, right? Where the ABMs and conventional models intersect, but kind of barely, right? Now, of course, this is just a question for inside baseball as to how these different modeling paradigms intersect. I mean, the real question is, how does the real world play into all this, right? Is the real world actually covered by some of the conventional models, covered by some of the ABMs? Or could it be, in fact, that the ABMs are still too idealized? Or could it be, in fact, that any situation where you actually prove a theorem may be so idealized that it's not very, very useful? And so maybe the only way ever to get to the real world is to use agents, to use ABMs. So you can have your priors about this, but I'm going to give a couple examples here which explicate this a little bit. So think about why we I just given the simple supply and demand answer, but think about now for the general equilibrium case of having permitting markets to operate at a large scale. Markets make everybody better off, otherwise people wouldn't participate in the markets. At equilibrium, everything's budget balanced, so there's no wealth effect. And so if everybody's made better off and there's no wealth effect, well, let's just have markets everywhere. The first welfare theorem says this is going to give us a Pareto optimal outcome. Thus, the more markets, the better from this point of view. Well, what is the ABM version of markets, or what is the theory of markets? And I've written here, I'm genuflecting to, I think, the new version of how we talk about this as Valra Mackenzie error de Brew, Mackenzie being a month earlier than error de Brew, if I'm reading the recent work on this right. So we have an arbitrary number of goods and agents, arbitrary preferences. There exists a market clearing price in general. We know this by the Brouwer and Kakatani fixed point theorems. However, as some of you may know, these theorems are not constructive. And so if you actually want to think about how to compute such a thing, we end up in this world of having PPAD. PPAD is a complexity class that's not quite as bad as NP, but it's almost as bad. And so it's unclear whether a real market could operate this way. Basically, computing that market clearing price vector is a very, very hard problem, growing exponentially harder as the number of agents and goods increases. So what's the alternative of an ABM? I've written here the conventional model, the conventional Arrow-Debreu model, just touching on the agent one. What if we just let agents trade in their own self-interest at prices they locally negotiate? This market clears because the sum of utilities is always increasing. It's going to produce a market clearing event outcome eventually. However, because prices are heterogeneous, some agents gain, some agents lose. So this has now much more ambiguous welfare effects, at least in terms of wealth. And it's caused by heterogeneous prices. But it turns out that such models of decentralized bilateral or k-lateral trade have very nice complexity properties. In fact, that they are generally speaking in the complexity class P, the complexity is not going to become exponentially harder as the size of the problem goes up. So on the one hand, the Arrow-Debreu model, it has nasty complexity, while agent-based models have nice complexity. Presumably, the agent-based ones are closer to the way the world really works. So I've written here these two models just barely touch because in the limits of the agents just stumbling on everybody trading at the right price. So in this kind of measure zero world of everybody everybody stumbling on the right price, the markets are the same. Otherwise, they are different and they have very little overlap. So this is just a concrete example of an ABM versus a mathematical model that have little overlap. Finally, the last example I want to go through here just conceptually is, many of you will know the hoteling model, which once again we teach to graduate students in undergraduate school. Hoteling asked, why is there a diamond district in New York where there's 100 or several hundred stores co-located within a few blocks? He modeled this as being, kind of a one-dimensional version with two vendors. And why do two ice cream vendors locate next to each other on the boardwalk, say? So they can split the customers is the answer. Now, does Hotelling's mathematical model in the Economic Journal from the 1920s it's not too formidable to follow, but undergraduates would have a hard time with it probably, and the graduate students can follow it. How does it extend to 2D or 3D or to having some larger number of firms? And the answer is, Champernowne's dissertation subsequently is in fact a high-powered mathematical workout for the simple 2D case, for n equals 3 firms. I mean, it's very hard to actually solve this problem beyond just a few firms. But it's of course a very simple thing to do, and some of you will know that very simple thing to do computation with an ABM. Some of you will know that this model exists in the NetLogo library, and you can make it any number of firms you want. N equals 17 if you want to try, and believe me, n equals 17 is very hard to do mathematically, easy to do computation. And of course, the main answer is that the summary of all this is that Hotelling is wrong about this. Hotelling is not right that the diamond district exists because of these kind of clustering effects that he describes here. Because when you run for example, many examples are known, but when for example, running the NetLogo library with 17 firms, you'll find that they don't all cluster together, but rather they break up into pairs typically, or some small numbers to divide up the customers between them. Okay, so but I'm going to end here just by saying, on the horizon, my feeling is that there's even a different kind of agentization that's coming. Until recently, the way social science has worked is we had some existing idea for how the social world worked, and then we got some new data and we modified the model a little bit to integrate the new data. But now there are some domains here where there are so many data that most of them are not explained today by any model, mathematical, statistical, ABM. And furthermore, I suggest that existing models cannot assimilate these data because they're not written with respect to the data, basically. And so the tempting thing to do, and with apologizing for the gross character of this comment, is to start over. But there may be some domains where we need to do this. And I'm just going to give one concrete example. Is my own work with how to get firms to happen at kind of full scale with a real economy that someone mentioned earlier. I mean, we have tax data today on every single business for the last 45 years. I have 6 million firms by 45 years, every record shown there. And the question is, how can we get a population of then workers at the right scale to form firms that look like reality? And in a sense, ABMs stand today as sufficient explanations for these kinds of phenomenon. yeah, of course we have this previous work. Coase and Williamson and Hart and Holmstrom have all won Nobel Prizes for telling us how firms work, right? So we're not saying that their work is irrelevant or that their work is not also an explanation. Rather, we're simply saying that the terms of that work that they used is not relevant to the new microdata that we have. Today, we explain firms along a different route, and then we can adjudicate. We can say, well, which explanations are most useful? Well, that once again looks at the data. Which, if you want to understand why the data has the structure it does, which of the competing models does a best job explaining those data? Say of which we have so many that we're just on the verge of explaining some part of it. Okay, so the summary of all this is that to a great extent, ABM has been around for almost 30 years now, 25 years. The default logic for many ABMers is to start by, in essence, rolling their own model. We're not going to necessarily dock too closely to what's come before. I'm suggesting that this agentization idea is both a way to link an ABM to existing models, but also it's a way to seriously constrain the solution space for this inverse problem. We're trying to figure out what the right rules are, because we're only going to search for behaviors that reproduce, the results of the theorem. So theorems. We're going to then say, once we've got the model agentized and we can get the conventional result, we can get George Akerlof's result that the market for used cars dissolves because of information asymmetries. We can now relax George's basic specifications and say, is George's result brittle or robust? And I think that my own personal feeling is that most of the conventional ABM criticisms evaporate in such a world like this, where we're just trying to reproduce the conventional results and then generalize them. And I've written here, developing agent rules is highly constrained when we're just trying to do this agentization scheme. The quick last bit of advertising here is that we're going to have a workshop on this topic in August. There's going to be an announcement going out a little bit later this week, so look for that. And we have a variety of people who are pre-committed to doing this. So we're going to have somebody presenting. My former student, Omar Guerrero, is going to present Akerlof's model of lemons. We have Kramer's O-ring theory of development. Someone had agentized that. We have some good work from computer science on Gauss-Shapley matching that's been agentized, how to do it in decentralized fashion. And there are several other examples we have coming down the pipe too. So with that, I'll stop, leaving hopefully a couple minutes for questions.
Great. We definitely do have a couple of minutes for questions. So if anybody has any questions, let me know. So Tim, it looks like there's a question from Tim Golden.
Okay, hey. So yeah, I of course did an exercise in this kind of agentization some time ago now.
Your dissertation, Tim, in fact, right?
Yes, my dissertation. So under your supervision, in fact. And yeah, I'm thinking of this in terms of this theme of bounding the search space. That's kind of my personal theme for this conference. It's an interesting way to think about it. That basically the idea was construct a model where the agents behave the way that the classical economist, said the way they said they were motivating their agents, and really the agents ought to do what they said, and the agents do. And then you start relaxing assumptions. You let capital be mobile. You have increasing returns. You do things that would break the math. It doesn't break the agents, and you get to explore these variations. So in some ways, like you say, we're limiting the size of the search space to something pretty reasonable. In some ways, I think it makes sense to think of it as limiting the search space socially. The world is only ready to accept results that bear some resemblance to the existing result. And so by docking to the existing result and then saying, okay, all you have to believe now is that my modification is valid and you should accept my result. There could be results, there could be answers in some completely different part of the space that we're not looking at, but this has the nice property of exploring kind of an area around a streetlight. Somebody has shined an analytical streetlight on an area, an illuminated part of the space, and this allows us to explore that illuminated area and find better, richer pieces of it. I don't know if that's a useful.
I think it's fair enough.
Analogy.
I think it's a good comment. And by the way, just so there are no, we don't leave people with the wrong impression. I mean, I was very happy to serve in your committee, but it was it was the late great Tom Schelling who was also providing many of the motivations for what you did.
He was there too, and Herman Daly. It was a pretty great committee.
Yeah. Anyways, just on to vis-a-vis what you said, vis-a-vis in terms of this slide here, is that right? I think it's too ambitious to say you're gonna relax everything all at once and expect to know where you end up, right? So to relax one or two things at a time hopefully helps people make some progress here, and it'll also help referees feel not too as if a model's trying to accomplish too much, that the model's too ambitious. If you can just relax a few things at a time as opposed to everything all at once.
Okay, we have time for one more question. It looks like Yvonne has a question.
Hi, Rob. Great talk. So what about agentizing two models that are trying to explain the same phenomena, and then figuring if pieces of those two models may encompass something better? Do you think that would be too ambitious, too complicated, or something that could yield better hybrids?
That's a good point, Ivan. Yes, I think that makes good sense to me. I think we're trying to think of an example of someone who's tried what you said, and nothing comes to mind right away. But I think that seems like a fertile approach. I think yes, right. To take a couple different models, and I mean we have had, as many of you guys know, in the ABM community, we did have for about a decade these model to model kind of workshop comparison events, and my sense was that we always learned a lot about when you put two models side by side and compare them. You always learned a lot both about the model approach, but you also learn about the underlying social thing you're trying to model. So I think there's value to doing that. But the specific thing you mentioned, I guess haven't seen it done quite yet. But so yeah, it seems like a very fertile approach to make progress.
Great, thank you, Rob. Thank you very much for that presentation. I think at this point, we're going to switch to the next talk just to kind of stay on schedule.